Cell culture is one of the major tools used in cellular and molecular biology. Bioreactors are known as one of the ideal methods to culture cells. Bioreactors provide a sterile environment, gentle yet thorough mixing, a precise and controlled delivery of nutrients, and accurate real-time monitoring and control for cell growth. However, bioreactors are expensive to purchase and operate and prone to malfunction. Alternative method for cell culture is using shake flasks. Shake flask is more cost-effective as it uses fewer resources and less expensive technology, and feasible for many simultaneous runs. However, shake flasks have smaller output volume and are prone to contamination. Also, it is difficult to monitor important parameters in real time. SBI's shake flask technology aims to fix this problem. Cell growth quantifier, known as CGQ, measures biomass using backscattered light detection. The backscatter measurements that are recorded continuously and automatically correlate directly with the manual OD600 measurements. Liquid injection system, known as LIS, feeds based on defined profile using negative pressure. DOT software connects CGQ and LIS to enable biomass feeding, graphs data for real-time analysis, and alerts researchers outside of the lab. The goal of this project was to validate and extend the scope of SBI's primary innovations, CGQ, LIS, and DOTS, and to create and optimize a reliable cell culture procedure that can give direction to the sponsor and consumers. To optimize and develop a procedure, we started by collecting the initial set of data from the bioreactor and shake flask without feeding. As initial control, we ran a triplicate of shake flask experiment with default setting of feeding trigger of 500 AU, 10% glucose feed concentration, and 150 RPM. Then we varied 3 different parameters: feeding trigger, feed concentration, and agitation rate. First, the feeding trigger was changed to 250 AU from 500 AU. In the initial run, there were 2 distinctive growth rate peaks indicating that the feed was injected too late. Decreasing the trigger ensured that the feed was injected while the highest growth rate was occurring. Second, the experiment was run with different concentration of glucose for feeding, 15%, 20%, and 25%. The 15% glucose and 20% glucose feeds yielded similarly high growth rates, but 25% glucose was too high of a concentration. 20% glucose was deemed as the optimized concentration because its growth rate was slightly higher than 50% glucose. Finally, the agitation was increased to 100 RPM from 150 RPM. After the change, the growth rate was significantly increased. After the optimization process, we were able to combine all 3 optimized parameters and create the optimized procedure. The optimized procedure had feeding trigger of 250 AU, 20% glucose feed concentration, and 180 RPM agitation. This optimized procedure displayed a significant increase of bacterial growth rate in comparison to the initial biomass feeding result. The optimized result has fulfilled the goal to validate SBI's innovations and to create and optimize a reliable cell culture procedure. The optimized conditions show the increased growth rate compared to initial conditions in both bioreactor and shake flask. However, shake flask showed higher growth rates overall. Potential future direction can be focusing on media and feeding profile optimization, as well as pH and DO monitoring to further improve growth rates.